Hello everyone, this is Dr. Ameen Eetemadi. I'm a data scientist from RSGDREAM. Welcome to our poster. I'm presenting on behalf of our team, Dr. Wang, Dr. Mason, Dr. Zhang, Dr. Curtis, and Dr. Pavlovic. This is a machine learning framework for delineating the parental inheritance of French American genetic communities. In Ancestry DNA, we help customers learn more about themselves as well as the communities around the world that their ancestors are likely from. We do this by identifying genotyped individuals that share DNA and thereby creating large networks of identity by descent. Iterative dissection of these large IBD networks using Laverne community detection algorithm leads to creation of smaller subnetworks, and we refer to these smaller subnetworks as genetic communities, which are stable and accurately reflect population histories and demographics. We can identify the genetic community that a customer is related to today, but it remains a challenge to identify through which parent an individual is linked to a given genetic community. And so we designed a machine learning approach to address this challenge. We analyzed genotype data, microarray genotype data from 22 million Ancestry DNA customers. Each genetic community, we characterized it by a set of reference panel individuals, and this set of reference panel individuals are determined in the community detection step. Also, community polygons are delineated for each community using the 19th century ancestral birth locations of the members of each community. Now, there are two important data types that are key to our approach. One is the unphased feature vector, which is created for each customer by quantifying the number of close to distant matches to each of the reference panels that are identified based on the diploid genome only. Also, we have two phased feature vectors for each customer for each of their haploid genomes that are identified. And so these two types of feature vectors are key to our algorithm. So here in the method section, you see that we first create these feature vectors. Second, we assign labels for the training, and these labels are assigned based on the reference panel memberships. So positive label, members of that community, of a given community, will get the positive label, and the members of other communities and people with very low French genetic ancestry will get negative labels. The last step, we select features and train the models using XGBoost. At the end, we get one unphased model and one phased model for each community following this pipeline. So inference of the parent of origin works like this, that we get the diploid genome and the feature vector is created based on that for the proband, and the community assignment is done using the unphased model. Then we will phase the genome, thereby creating the haploid genomes for the proband, and we infer the parent of origin from each of the haploid genomes, thereby connecting the person and identifying the parent of origin. Here are a few highlighted findings. One, we're able to identify the parent of origin in 95% of the cases. 85% of the cases were single parent origin assignments, and 10% were coming from both parents. And in 5% it was undetermined, and this was correlated with the completeness of the genome phasing. And the children parental designations actually matched their parents' unphased assignments close to 98% of the time, which shows that our models are highly concordant for children and parents. Here's an interesting community, which is the Canadian islands of Cape Breton and Newfoundland community, which had the highest proportion of inherited assignments from both parents. This is highlighted here on the map. This is an island which this is typical actually in populations with low migration and high rates of endogamy. So in summary, we present a machine learning framework for inference of genetic communities and the corresponding parent of origin using haploid and diploid genotype data. Thank you for your attention.